All right, we're going to be working on Unit 2 today, so if you guys can go into that unit folder, I think that would be helpful for you. Up on screen right now, I kind of want to show you the typical layout that you'll see for most of the course. This is the first unit that we're working on here, where it's really regular content from the book, and this is going to kind of set our workflow for the rest of the semester. Whenever we are working on a chapter in the book, I'm going to be putting the topics that we're addressing right at the top of each unit folder. That's my pattern, along with the PowerPoint provided by the publisher. Now, sometimes I do take those PowerPoints and alter them, but you know what? This is my first time using this book, so I really don't know what they're like, so I'm going to kind of go with it and see where they're at, and I may end up making changes to them in the aftermath. You might also see me, as we go through, skipping over some slides, or maybe spending more time on some slides than you thought I would, because I think certain concepts are important. Some of the stuff that we're going to do in here is going to mimic what we did in the previous unit, and with those, I might tend to go a little bit more quickly, although I might end up focusing on some of the things that we didn't talk about. Additionally, I will hopefully add videos here as soon as I get done with them. I know I haven't been good about it this semester so far, but it's on my to-do list for today to upload stuff to YouTube and get it all linked up. And then I want to turn your attention to a couple of activities that I have posted here. Now, activities are exactly what they sound. They're nothing that's obligatory, but things that you might want to consider doing, and I think is just good practice. Which is why I put them out there. And it's not to belittle whatever IT skills you guys already have. I get the sense from all of you that most of you are pretty sharp on this stuff already. So please understand that I'm not trying to minimize whatever knowledge you think you have. That's not the intent here at all. The truth is, even when you're covering topics that you think you kind of already know, and this has been my experience in life, right? And I get it from teaching a lot. It's like, hey, I really think I know this. I'm going to teach it to the students. I'm on it, And then all of a sudden I learn something new. The students teach me something new, or I read some little tidbit I've never heard of before. And you know what? It's all those little pieces you start to stick together that make you an expert in the field. People will often say, Ty, how do you know all this stuff about all this stuff? And I'm like, well, I've been doing it a hell of a long time. And I've done a lot of different things in my career, so that's how I learned those things. All right, now the first activity that I have posted here is one I do want to talk about because it becomes important when we start to code. Really what it comes down to is, where are you putting your files when you're doing your schoolwork? And I'm not one to force you to do it any certain way, but I can tell you what best practices are, both from experience and from what other people in the industry do. So the first thing I want you preferably not to do is to put all your work on a flash drive. Now the sad thing is when I started here about 6 years ago, every syllabus in the IT department said required equipment, flash drive. And that was you see I'm like slapping my hand on my forehead right now. People in the video can't see that, that's why I said it out loud. To me, that is such backwards thinking. It's like using a floppy disk, right? Or burning your stuff to a CD. I mean, yes, it does work. And there are times and places for those things. But the reality is, my preference for you as students is that you come in with your own equipment and save stuff right onto your own hard drive. And then on your own hard drive, to do something really, somewhat basic. Yeah, you can see what I was doing. Sorry. Yeah. All right, go ahead and install it. Okay. But what I do on my machine is, if I was working in my traditional old-fashioned way, this is the old days, and I'm talking like a decade or two ago, what I would have done in the past is I would have went to my documents folder, and I would have created a folder called Gateway, right? And then inside that folder, I'd probably make another folder. And some students will make semester folders, so they'll say like fall 2019, and then put their courses inside there. That's fair. Or I might just call it like Python. And then all the stuff I do, and I even misspelled it, doesn't matter. I would just throw them in. Just an example. The better way to work these days is for you guys to use cloud-based storage. So what is cloud-based storage? Somebody give me an example. Google Drive. And for students, I'm going to tell you what, it makes a whole lot of sense because attached to your Gmail account, and I'm going to bring my Gmail account back over from the other screen. You just go to your little waffle icon up here in the corner and click that, pull up the drive, and then you can access your files. So I'm going to just give you a what-if scenario. You're sitting here in the classroom and you're using a school machine instead of your own, right? And that happens with a lot of people. What is a smart way to work is to create a folder inside your Google Drive, just the way I did in the Documents folder. Call it Python, have subfolders any which way you want, and then when you're done working on that workstation here, you can just take your stuff and drag and drop it in. So I mean, just to give you an example, I'm going to take this silly misnamed Python folder, and you see I'm just dragging it and dropping it right into the interface, and it uploads. So you can work at one of these school machines, throw your stuff in a folder on the desktop or wherever. When you're done, log into your email, go to your drive, drop the stuff in there, you're golden. That way when you get home, you can still get to it. For those of you that are using your own equipment, you can still use that same approach, but instead of working directly through the browser, what you could do is load up Google Drive onto your machine and have it run memory resident in your system tray. Now, I have a little bit of a thing here because I'm using a school machine right now. Because my Google Drive here at school is an organizational Google Drive, there's actually a different piece of software we use than consumers use. It's called Google Drive File Stream. And the truth is, as a consumer, you can use that one as well. But that keeps all your stuff out on the cloud. You can see I have a little icon right here that's got the Drive File Stream. Right? That just shows me anytime I'm saving something into my Google Drive here locally, it's automatically propagating up to the cloud and to every other machine that is connected to it. So a lot of you that are Windows users already, you probably have OneDrive. So I have like OneDrive sitting right here, and this is my personal OneDrive. That's why I'm not clicking on it, because I don't want you guys to see what's in there, frankly. But I could often use that as my cloud drive. That also runs memory resident, does the same thing. I have a folder on my machine that behaves like a regular folder. Every time I drop a file in there, pushes up to the cloud, pushes out to all the machines that are connected. Those are not the only services that do that. Dropbox, OneDrive, Google Drive, SugarSync, Box. I could probably name a dozen others if I keep going. And they all work the same way. But even if you just use the browser-based approach on a school machine, that's fine, because you don't want to load up your Google Drive software on a school machine. That makes no sense. But having that capability is important to me, and I think it should be important to you to organize your work so you can find it quickly. All right, that's going to kind of be like my entire spiel for this. But what I am going to do preemptively here is, you see I have my Google Drive file stream linked up, and I forget if I've created a folder or not. So I have created a folder for my class. So you see all the courses I teach, I've created folders for them. Yeah, I've taught that many classes here, believe it or not. And then I have a folder that contains all my stuff. Now what you might want to do, now since I'm going to teach this class many times probably, I'm going to make a new folder inside my folder called 2019 Fall. And so that's the folder where I'm going to put my code, the computer code that I create during this semester. Inside that folder, I might also opt to create subfolders, perhaps for each unit, because what you're going to see is every chapter we do, there's going to be probably more than one coding assignment that you're going to do. The last thing you want to do is put everything into one folder and then hunt to find them. The other thing that you might want to do is, as you're creating your programs, is give them meaningful names for the files. So for example, in Blackboard, what I suggested is, let's say I was working on exercise 13.9, and the point of it is to calculate interest. I might name my file like this, like I got in bold. So basically, I find some sort of a way to designate which assignment it's related to and maybe give it a meaningful name. That way, when I look at it next year, I can actually find it.
So
right?
I was only half paying attention to the first part.
Which part did you miss, Tom?
Cloud storage, like you said, we could just do Google Drive, right?
Yeah, that's one way to do it.
And just submit a link, right?
I didn't say that. We'll talk about how to submit it separately.
Okay.
That might potentially be one way you can do it. So the question was, if you didn't hear it in the video, so we use cloud storage and then submit a link. I'm going to say perhaps at this point in time. And I'll show you my preferred way to turn in homework when we get to that point.
Okay.
The other part of this, frankly, is as professionals, you might also opt to use a different approach. Does anybody know what professional programmers do with their code when they write it? What do most of them do? Well, they use what we call source repositories. That's a fancy way of saying cloud storage for code. So there are websites like GitHub or Bitbucket. And really, once again, there are many services like this. So you, instead of using your own cloud storage to store your code, you can use a service like GitHub and store your code up there. The only issue I have with those services is this. GitHub, which is kind of like the professional's choice, is not a free product. If you use the free version, everybody can see your code. You only get privatized folders and stuff if you pay. There are some services, and Bitbucket at least used to be one of them, I haven't checked it in a while, they allow you to privatize your stuff without paying. There's also other services that programmers use that kind of combines file storage and collaboration, like Microsoft Teams or Slack, and we may experiment with those as we go, but that's not really my focus here. As a professional, if you worked in a coding house, you probably would be forced to use a service like GitHub on purpose, because it offers you a lot of different advantages aside from just a place to put your files. It allows you to, for example, try something before you actually bundle it back into what you're doing, and that's called a fork, for example. So there's some really cool tools that way. All right. Any questions on that so far? You guys are cool? So if you haven't done so already, even if you're working on a school machine, you might want to actually consider, when you're working here, creating a folder on the desktop. If I was doing a school machine, that's what I would do, because it's easy to find. And then whatever you do today in class, drop it into that folder. When you're done, log into your email, go to Google Drive, drag and drop it in, and you're good. Really want to use the flash drive? Great. My advice, if you want to use portable media, attach it to like your car keys or your cell phone. You know, things that you're not going to forget. You know, but you know, sometimes you forget your phone too, right? I've had some students that are really clever and have realized that, you know, I can take a sync cable and just plug it into the machine. I can use this as my drive and just transfer the stuff right to my phone. Okay, that's great until somebody steals your phone, right? Right. All right. So that I mean, so it's just a big flash drive. All right, that's the thinking. All right. Right. With a monthly bill attached to it, right? All right. The other activity I've got pointed out here is one that I'm kind of going to demonstrate as we get rolling with the lecture. How many of you have the ebook, but ebook only? Okay, I'm ebook only. Those of you that have the hard copy, did you know there's an access code, like a card that comes with your thing with the access code? That gives you access to the electronic version of the book too. And what I've discovered with the ebook is it has these interactive exercises built right into each chapter, where you can like work with Python code and hit a button and tells you if you're doing right or wrong right inside the book. I think that's kind of cool. It's a little cumbersome, you know. I've been reading through the book and working through them, and I try all of them, and then after a while I was like, do I have to try this again? But if you're really trying to learn a concept, you have the ability right inside the textbook electronically to try out what they're talking about. So I think that's really kind of neat. So I'm going to point you to that as I lecture. But for right now, here's my goal for the rest of the day. I'm going to pull up the PowerPoint. We're going to talk about some concepts. As we go through the PowerPoint, I'm going to do some demonstrations. And then hopefully we can get done fast enough that we have time to start working on the homework. And then I can, at the very least, show you how to complete one assignment and turn it in. That's the goal. As we proceed in this class, I want to keep reminding you guys of this, that I'm hoping we get to the point eventually where we flip, where all we do is come to class and code. I'll just put the assignments out there. We'll come in and work on them together. That will happen more as we progress through the semester. All right, let's move on to the PowerPoint. I'm going to just click it and download it. I'm not a huge fan of doing it in presenter mode. I'm just telling you that up front. And if you guys aren't familiar, when you're like multi-screening and you do the show the slideshow kind of thing, what happens is the screens kind of lock out, and I kind of don't like that, so that's why I often do it the way I do it, and I do enable editing. I know you guys are familiar with this product for the most part. If you aren't, I mean, there's tutorials out there on how to use PowerPoint. But this is what I usually do. I pull the screens up like this. I don't care that you see what's coming up. Yeah, this is 52 slides. I promise to go really, really fast. With some people, it's like, oh no, PowerPoint, I'm asleep. I'm hoping that's not the case. All right. The other thing I do want to point out is a little section that I hid here for those of you that might actually prefer it. I do get students like this that they kind of like don't bother with the textbook much. If the PowerPoints are good, they just use that as their book. And then when they're in class following along, if they have the PowerPoint up on your screen, they have the notes section down here. You can type stuff in for yourself if it helps. Just pointing it out. Maybe you guys already know that. Don't mean to belittle your knowledge in any way. All right. So goals of the chapter are these. And we are going to talk about all of them. But really the fun part is actually getting to the point where we're finally coding, right? And getting this ball rolling. All right. We talked about this last week, this word algorithm. All right. And notice, a step-by-step description of how to solve a problem. Most often we hear this word associated with computer technology, but really it can apply to anything. If you talk to anybody who's a professional in their field, and pick a trade, plumber or something like that, they have certain algorithms that they use to do their work. Why do you put a vent pipe here and not there? Well, so your toilet will flush, and they know these things, but they have a step-by-step that they follow in their disciplines. It's not just a computer thing. I always like to tell people, and it's probably because of the way I was taught when I first started formally studying computers. I did a lot of self-study because somebody gave me a computer and I had to figure out how to do stuff with it. So I bought books, I read every manual I could, and then I went to school and formally was taught by somebody that at that time, in the mid-'80s, had been doing it a really long time. And the thing she said to me, and it was a female, she said to me, computers are just dumb machines. They don't know how to do anything unless you tell them how to. We have this assumption that because we got Siri and the Google Assistant now, or Amazon Echo or whatever, that we can just ask it a question, it does it and it gets it. But that, it's really not the case. It's all based upon computer programs that we write, instruction sets that human beings create for the computers. If we get to the point where the computers are intelligent enough to program themselves, then we need to watch out. Right? Because it's like Skynet and all the science fiction stuff that you hear about. All right. So the whole point of what we do to create computer programs is to create the instruction sets that perform specific tasks on a machine. All right, now we're going to talk about hardware and software a little bit. All right. Whenever we talk about hardware, you guys should know this stuff. But here in the web program, we just changed our degree. If you took the old version of our degree, you guys would be obliged to take a course called IT Essentials, which all the networking and CSS and cyber students take. And I see you nodding your head because you have to take it at Lakeview. And that course, what it did is it taught you about the hardware and the key operating system software for the most part. You would actually take the machine apart and you would see what a CPU is, what the memory is, what the motherboard is, the power supply, all those things. They're just physical components. Yes, sir?
Was Miss Becker so deep that class or not?
Ms. Becker?
Yeah, she taught it after effort.
I wouldn't know. But yeah, they do teach in some of our high schools in the district, but we teach it here at Gateway. We decided in the web program that it was more important for you guys to get more programming than to learn about hardware, but you still have to kind of understand what these things are. I encourage anybody that's working in IT to get some sort of a grasp on what a CPU is, what it looks like, what RAM is. Because if you understand how a machine works, it's a little bit easier for you to program for it as well. Not that it really is necessary, but it's important. The CPU, of course, is what we call the brain of the computer. It is a chip that's about like this big, maybe like 2 inches by 2 inches. It's wafer thin, and it holds billions and billions of transistors. Billions and billions of transistors. And I always like to kind of like bring up in Google some basics here. So this is like my informal presenting mechanisms, right? And I know your book's got a picture of this thing, right? Like ENIAC, and I think it's maybe even this picture here, right? Where they show these people like standing in these rooms, and I mean they're working with a room-sized computer. ENIAC, which was built right after World War II, was the first fully electronic programmable computer. Okay, so that there's some kind of illusions in what I'm saying here. It also indicates that there were computers before this point that were electromechanical or completely mechanical. In fact, really the first computers or devices that were used for computing was this. You've seen this spiel before, David, haven't you? Right? It was the abacus, and this dates back thousands of years. It was the first device that we know of that was specifically designed for doing math. And here's the key, folks. Computer hardware is really designed for doing math. In fact, a CPU, all it can really do is add. That's the only thing that CPU knows how to do. Now, how do we build a computer that can do all this stuff like, here I am downloading the Battlefield upgrades, right? So I can play video games. How do we go from adding to playing Battlefield? Well, adding also leads to subtraction. Okay, so the inverse of adding is subtraction. So what does it take to multiply? You add a bunch of times. So it's multiple addition. What's division? Multiple inverse addition. See how, and then everything extrapolates from there. And then it's human beings that are clever enough to convert all the different things we need to do into basically just adding, and then ultimately storing values as well. But it all started with the abacus. From the abacus, we went to a lot of different devices, and from there we went to this thing called the Jacquard loom. And why this device is important is this. So it's like, 1600s, something like that. This guy weaves rugs, right? And, he figured out a clever way to hook up his loom to a water mill. So like we have like river powering this mill wheel. It makes this thing spin, and it drives that loom. And the way a loom works is you have like threads, and then you shoot a thread through, then you alternate the threads, shoot it through again, and depending on what colors you use, you come up with a pattern, and you have a piece of fabric. He figured out a way to automate the process so that he could like churn out a rug in like minutes instead of like 3 weeks or something, right? And then he got really clever, and he developed this part of it, Notice what those are? Those are wooden cards with holes punched in them. So what those did, he would take those cards, and those cards would represent the patterns of like what color of threads would trigger. So he programmed the rug. So he established the pattern for the rug in a series of punch cards, strung them all together, would hit the lever on the thing, the wheel would run, the threads would go automatically, and all of a sudden he went from like being able to like create a rug in like even minutes to even like shorter time. I don't know how quick he was doing it, but the beauty of it was he was able to reproduce the pattern. And the reason that he did that is the King of France came up to him and said, I love this rug. I want 1,000 of them for my palaces. And I was like, I don't know how to do that. And this is how he figured out how to do it. Now, why this is important is because that allowed us to store a set of instructions, step by step. Should sound like a flowchart or pseudocode. And then we had this guy named Charles Babbage and his analytical engine. All right. So this guy, this is late 1700s, early 1800s. This guy had this thought. Wouldn't it be cool if we could build this machine that could do math for us? Right? And so he had drawn up theoretical plans for a physical computer, that just like gears and wheels and pulleys and knobs and levers and whatever, where he could like flip a couple of switches or whatever, turn the crank, and then something would happen, and then it would flip the lever some other way, and it would give you the answer to your math question. The sad thing is, he was never able to actually build it. The stuff that you see here are people that built it well after he passed away. More importantly, he had this lady, Ada Lovelace, right? She was the first computer programmer. Sorry, guys. Women did it first. And what she did is she wrote the first computer program. In fact, she figured out how to write an instruction set. And this is the actual first computer program you're seeing right up on screen here. And if I can get that bigger, there's her face. There it is. So this is the actual code that she wrote. So what she did, the guy had the theoretical design for the machine. She wrote the code theoretically that would drive that machine. And if you look really carefully at this document, take a look at the columns. There's columns for variables, data, and she's got formulas in here. And basically, she took like these complex like calculus concepts and transferred them into what we would need to do on a machine in order to solve it. She figured out the instruction set. This document, I think, sold for like $250,000 like a year ago, because it's that important in history. This concept of the analytic engine, which they ended up building eventually, kind of parlayed into something even more interesting. We had these people at the end of the 19th century that took a combination of the concepts from the analytic engine, the mechanical computer, combined it with the programmability of the punch cards from Jacquard's loom. And what this guy's task was, he worked for the U.S. Census Bureau. So the census says that we have to go out every 100 years, every 10 years, and count every single man, woman, and child in the United States, and report back to Washington, D.C., and here's the report, Congress. And that would dictate how funds were allocated and who got what resources and that type of thing was very important. During that time period, the United States was growing really fast. We had just developed the railroads. People were moving out west. You know how hard it was for these people to go out and count everybody? Like if you lived like out in the hills of Montana, it's still hard to get there. Imagine how much of a pain it was. And the problem was that it would take them usually longer than 10 years to tabulate the data that they collected, because they spent 9.5 years of it gathering it. So what they did is they would take that data and punch it into punch cards and feed it into this device that he created. So it was a mechanical computer that was able to read punch cards and do tabulations. That device there led to the foundation of the first IT company. You know what that company is called? They're still operational. IBM. That's how IBM began, late 1800s. And there's a whole stream of machines. And you may have seen machines like this. Okay, well, those are modern ones. Maybe you've seen something like this, right? And I remember actually like going into like the Kohl's food stores by my house when I was a kid, and they had mechanical cash registers. Well, not exactly like that, but kind of like that, where the ladies would be like, and pull a lever, lever. And it was just a physical adding machine. Didn't even have electricity. We're not talking that long ago, folks. That's just a mechanical calculator. So we went from those mechanical calculators to ENIAC, and then all bets were off. All right. So I think that's really kind of important for you guys to know historically, because I don't know if you'll get it in any of your other classes. And if you do, fantastic. I'm glad. All right. But the hardware, we went from all those clever people doing stuff without all the advantages we have today to develop this amazing technology we're using right up on screen right now. The central processing unit is the one that does all the heavy lifting. That's where the instruction sets are processed and data moves around. Okay. But despite that, the CPU is still just a physical machine that doesn't know what to do. We must write the code that tells it what to do. When we buy a computer, walk into Best Buy or whatever, we buy a laptop, bring it home, it's already loaded up with all this stuff, right? But can you imagine if you're just given the machine and nothing was on it? You got to come up with that instruction set. So we're benefiting from all the work of the people that have come before us. All right. Computers have a couple of different things, and the reason I like to show this chart here is it shows you what happens in what we call a systems approach to IT. Typically speaking, when we're dealing with IT, and I'm hoping this picks up in the recording here because I'm walking away from the computer, is we have what we call inputs, we have outputs, and in the middle we have processing, okay? And that's kind of what this diagram is trying to show you. So when we look at it on a hardware level, we have like a mouse and a keyboard where we put input into the computer. On the inside of the machine, the processing happens, the magic that makes it all go. And then we have outputs. We either like put it on paper, or we put it up on our screen, or it comes through our speakers. Output. Same thing happens when we start writing computer programs. That input, processing, and output paradigm applies. So a lot of the programs that you're going to build, you will be thinking about what inputs do you need from the user? Because the user is going to interact with your program. What's the program going to do in the background? What processing is it going to do? And then finally, what output is it going to give you? So the concept transcends from the physical to the theoretical and to the software layer of it all. So that's a fairly important thing. Now, I'm not going to go through all these details of the CPU and storage and stuff, but I do hope that you read this stuff in detail. I think the book does a nice job of explaining it. I do want to explain one difference, though, that I might ask you on a test, which is why I bring it up. When I say, hey, what's the primary storage on your computer? Most people will tell me what?
RAM?
Well, RAM is the correct answer, but most people think of it as your hard drive, right? The truth is RAM is where primary storage is. That's where stuff sits in memory so we can actually do stuff. Secondary storage, hard drives, disks, flash drives, whatever, is a place where we store things long term. Primary storage is typically volatile, secondary storage typically is not. All right. Let's talk about this a little bit. Computers are built around kind of like the binary number system. Ones and zeros. That's really kind of like all they really understand numerically. The truth is, when a computer operates, we have negative pulses and positive pulses of electricity that form the ones and zeros. And because they're working on basically a binary state, we are forced to use kind of binary number systems to kind of build all the things that are attached to computers. So if I was to create characters on the keyboard, every time I press a key on the keyboard, it actually sends out 8 electronic pulses of positive and negative to represent that key press. And those 8 bits of information turn into a byte. And that's kind of what this is trying to explain. So 8 bits is what it takes to do one single character on a keyboard or in a document. When you start to add to that, it's all multiples of 2, but usually when we get to 1,000 bits, and it's actually 1,000, 8 bits forms a byte, 1,024 bytes forms a kilobyte, and then you just kind of ramp it up from there. So when we talk gigabytes, which is where we're at most commonly now, we're looking at how many? About 1 billion bytes. And then times 8 for bits. That's kind of crazy to think about when you're trying to put things together. All right. So part of what we do as programmers is come up with the instruction sets to tell the computer what to do. When we code, we are going to be coding at what we call a high level. Computers don't understand the words we type. So anything that we type as an instruction set needs to be converted to what the machine understands. That happens in the background. We will work at a high level. All right. Software is what we load onto a computer to make it do what it does. And what we're doing as computer programmers basically is creating that software. There's a couple different categories of software. Really, they're interrelated, but we think of software as 2 basic categories. One is operating system software that makes the computer do what it does. So like Windows, or if you're using a Mac, the Mac OS, or if you're using a Linux box, whatever distribution of Linux you're using. If you're using a smartphone, Android or iOS, those are the operating systems. Software, application software is the stuff that sits above the operating system that you use to do your work. Your email program, your text application, your video game, whatever it happens to be. All right. Now we had a little bit of a session here on algorithms earlier in the previous unit, so we've already talked about this. But one thing that the author does that I think you might want to focus on a little bit, hint hint for a test question or something, is the formal definition, because it does not come from thin air. An algorithm, per the author, is unambiguous, executable, and terminating. So in other words, look at what unambiguous means. There's no assumptions. No assumptions are required to execute the algorithm. So, in other words, what we decide to do, there's no other way to do it. That's the way we're doing it. It is very specific. Executable. It actually works. You can actually do the steps that you've outlined, whatever those steps are. And then at some point, you find a way to end it. So those are 3 terms you might want to flag for testing. All right. I think we've talked about some of this. The author does go into an example, and I think that we've done this well enough in the previous unit. Like he says, a simple algorithm to get yourself a drink of orange juice, right? Get a glass from the cabinet, go to the fridge, grab the orange juice, pour it in the glass, put the cap back on, put it back in the fridge, drink, you're done, right? Pretty simple. The problem that some people have with beginning to write computer programs is the level of granularity that you have to apply to solving the problems that you're faced, because you don't usually think about problems in super detail. But the trick to it, frankly, folks, is to break it down into little pieces and solve each piece separately, and then put all those pieces together. That's the trick to it. They have this example, and for those of you that read the book, I would really like you to take a look at this. I'm not like giving you an assignment of this nature, but I think it's a great example. So it's like, this is a thing that you might face as a person out in the field. You might want to buy a car. Now, I didn't drive my normal car today. I usually have this really fuel efficient little Volkswagen that I drive. I get almost 50 mpg. and I hardly use any fuel. And I've been using our other car the last couple of days, which gets terrible gas mileage. And I've burned through almost a half tank of gas in 2 days coming to work, where with my other car I can commute for 2 weeks without filling up. And this is the kind of thing that you might be faced with. But when you're looking at a car, you might look at the one car that guzzles gas, and it might be a whole lot cheaper than the other one. So when it comes to upfront money, you're like, I'm buying that cheap car. Look how nice it is. Look how big it is. And then you start driving and, oh my God, this thing costs a fortune to operate. And so there's like this balance. And basically what this algorithm is figuring out that balance. What does it cost to buy the car? But then more importantly, what does it cost to actually operate it? What does it cost to insure it? These are things that you have to figure out. So there's an algorithm for doing that. And what he walks through here in these slides, and I encourage you to read this, is the procedure for doing it. Now, if you set up pseudocode correctly, the pseudocode will be really generic. So it doesn't matter, it's not tied to the specific price of one car. And when you guys were doing some of your pseudocoding and flowchart assignments, the one thing I noticed is some of you hard-coded values in. You shouldn't do that. You should set it up so that it can generically take any information, so I could put the price of any car in there and have it figure it out. So it could take any two cars at all, what's the purchase price, what's their gas mileage, dump them into the algorithm, and it will tell you which one is the better value. Now really, if you really start to think about it, there's other factors too, like what does it cost to insure it? You know, what does it cost to do maintenance? Blah, 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 right? So you can take that. All right. So what he shows us here on the last slide is how to go through and set up the algorithm. And he actually takes it pretty far. He's got like looping built in here. He's also got conditional statements built in here. So this is actually kind of advanced pseudocode, and I'm not expecting you guys to write this at this point. But when you go to the end of the course, come back to this and take a look at it and go, oh, I see. Not that you can't latch onto the concepts right away. He provides a second example related to bank accounts. And this is one of those classic business things. And I was a business major originally before I became a computer person. And this is one of those things you learn. So if I have $10,000 and I put it at the bank at 5% interest, how long does it take for me to double my money if I don't touch it? And you know what? There's a formula for it, right? And he shows you what the formula is and how to accomplish it. And then the task as an algorithm is to break it down and to figure out how long does it take. Well, the answer is at 5% interest, 15 years. You can double your money. All you have to do is let it sit there. How do rich people get rich? They let their money sit in the bank. Other people borrow against it and they earn interest. That's how they get rich. Isn't that interesting? Of course, if you don't have the money, you're kind of SOL, but if you have the money, great. All right. Once again, he translates it all to pseudocode. And then here's the important takeaway from all the pseudocoding and flowcharting stuff, folks, is the reason we pseudocode is to pre-solve the problem before we start to write computer code. Because the place to solve the problem is not within the code itself, but it's in the process prior to writing the code. Now, when you guys sit down and write your first programs, the first things we're going to do is like, hello world, right? Not a big deal, right? You don't need to really write pseudocode for that. However, if you were going to write a program that does some of the stuff that's explained here, those are complicated problems that will involve a lot more thinking about the little pieces it takes to make it work. I don't know any programmers who write big applications that don't do some sort of like troubleshooting and problem solving either graphically on paper or on a computer software or just typing out stuff or jotting it on a piece of paper. It really is a necessary step. It's also a step that you guys probably employ in your day-to-day life and probably don't think about it much. Like one thing I did before I started class, I want to make sure I didn't forget anything, so I made a pseudocode for myself of like what I need to talk about. And I've got some stuff crossed off already. I'm doing pretty good. Kind of running out of time, but I'm doing pretty good. Trying to think about that. All right. I want to take a 5-minute break now, folks, and we're going to come back and finish up. This is a really logical stopping point. So please stand up, walk around. We'll see you in 5 minutes. Okay, welcome back from break, you guys. We're going to talk really quickly about the Python language and then we're going to start digging in to the IDE. I will tell you that currently on my second screen, I forgot that I didn't teach this class last week on this computer, so I'm actually installing Anaconda and the Spider IDE. And that's not something you're looking at, but I'm watching all the files on zip right now. All right, let's talk about the language that we're about to learn. Python is definitely what we call a high-level language. The intent of it is to make coding simple for us as programmers. All right, and it's probably one of the easier languages to learn, which is one of the reasons it's become so popular. But aside from it just being easy, it's actually super powerful at the same time. It's really been kind of taking control of a lot of areas of IT. Because of the way it's engineered, it actually can run on literally any platform. It uses a strategy similar to what Java uses. In other words, we're not writing code that's native to the operating system. We're writing code that's native to the Python virtual machine and the interpreter. And then there's other layers beneath that convert it to a point where it can actually run on the operating system. For those of you here in class, I did this quick little diagram here, and my marker kind of was fading out as I was writing it. But we start with our programming code, basically what we create, and then there's a layer underneath that's called the interpreter. Now, because Python is not necessarily a compiled language by default, like JavaScript, it just runs. It gets interpreted. So whatever commands we type is interpreted, and then that allows it to run inside what we call the Python virtual machine. So what that means is there's a virtual or a simulated computer system that kind of runs on top of Windows that runs the Python programs. And the truth is, most computer programs kind of run that way. They're kind of isolated from the core of the operating system. There is a compiler ultimately underneath that does convert the instruction sets to what we call bytecode, which is what the computer processor can understand and execute. And that's what makes it work on the operating system. There is a whole section of that in your book, and I'm hoping that you read it. Might be some questions on your exam or tests about that, so once again, a hint. The other thing that we'll talk about is the guy that actually invented the technology. So there's this guy named Guido van Rossum, and he actually developed the language in the early 90s, and he's just a guy who was tasked with writing scripts basically for doing a bunch of mundane tasks, and he didn't like the languages he was working with because the stuff that he was trying to do, it just seemed like it was way too much effort to do the simple things that he was trying to accomplish. So he developed this language to kind of help with that process. And the truth is, Python is used by a lot of professionals for exactly that purpose, for what we call scripting, which is to write simple, sets of instructions for computers to perform automated tasks, like maybe do a backup or transfer files or something like that. And so he developed this language to do that. When we sit down and we actually try to write actual code, folks, we use a thing called an IDE. And that, of course, is an acronym that stands for Integrated Development Environment. So what that means is we will have one software tool that will allow us to create the code and run it and debug it all inside the same environment. In the old days of computer programming, and you know what, even in the modern days, one way that you can actually create code is you can just bring up a simple text editor, and I'll just bring up Notepad++, because that's my favorite simple one. I'll create a new file here to get that off the screen. And you write whatever code you write in here, and some of the stuff we'll do, some of the simple programs we'll write initially will be like this, very, very simple commands. And it's already got an error in it, see? And then we take that file, save it, and you don't have to follow my process here. This is just to demonstrate. I'm just going to throw this on my desktop right now. I'm just going to call it whatever, one of my favorites. And then Python files always will end with a two-letter extension of .py for Python. Okay, so once you would have created a Python file like this on a machine and saved it as a text file, you would then bring up your command line, navigate to the folder where it's located. You gotta spell it right though. Find the file, make sure it's in there. I called it whatever, so it's right there. And then you just simply issue the command Python and type in the file name. Oh yeah, see, Python's in the process of being installed right now, but if it was properly installed, that would run the program and it would put hi up on the screen. That's how you would do manual programming, console programming in the old days. And when you're in like the Java class here at Gateway, we make sure that you get a little bit of experience doing that because, you know, frankly, sometimes you'll be out there in the field working on like a system and you need to fix a program and just get it to run and do something. And they might not have an IDE on it. Why? Because maybe you're working on a server, right? There is no IDE present. And you have to know how to get in there and tweak the code and make it work. So that's why that's important. We are not going to do that in this class because frankly, I don't see the necessity for it. Python doesn't need to operate at that level. Additionally, the console, and when we talk about console programming, that's when we're programming for command line like this. There's a console built right into the IDE that we're going to be working with. So why bother to do it a different way? Now, on my second screen here, my install is getting there. It's at like the 89 percentile right now of completion. So in the meantime, I'm going to go back to the slideshow and talk about something that's kind of interesting. First, let's go back to this slide. So the IDE will have three main functions, and one of them is you have a code window where you can see the code that you're typing. You'll have tools to help you type that code. A good IDE will do this thing called IntelliSense. So as you're typing your code, let's say if I was going to issue the print function, I would type the letter P and it would start to recommend what I might complete it with. And I'll tell you what, that's a great tool because it helps speed up your coding. And then the other thing you'll see is that it will automatically kind of like highlight and help you make your code correct. So when I was typing in Notepad++, you guys probably noticed that like right away, like I forgot to put in the second double quote, right? Which is bad, very bad. What the IDE would do is right when I hit that first parentheses, it would create the second one for me so I wouldn't forget when I put in the first quote. It puts the second one in right away and puts my cursor in between to help me not make mistakes. That's one reason why we use IDEs. It is good to know the manual, but it helps. It also does color coding of certain things. Notepad++ does that too, and I find that really helpful. So it'll take like certain keywords and make them blue. Certain things will be red, so you know what you're looking at on the screen. And then if you create a comment in your code, it'll gray it out, so you know that it doesn't really affect the operation. The other thing that the IDE will do for us, it will help us indent the source code correctly. Python, unlike some other languages, relies on indentation to indicate the hierarchy of the code. Most other languages, if people are indenting, it's more for their own visual sake than for the sake of the language. In those languages, we'll typically see things like semicolons and curly braces to kind of block off code. That's not how Python works. All right. Another thing that you'll see is what they call the output window and what I was just calling the console. Kind of an interrelated term. But it's just a part of the screen where you'll see that output. So instead of seeing like that green screen that I had up, you would see the console window, and it's all in the same environment. Another thing that's built into the environment are the debugging tools. So as you type code on the fly, it will highlight mistakes you're making. And then if you don't catch the mistakes and you try to run the program, the debugger will also kick in the output window and show you where the mistakes are and give you a message. Sometimes they're cryptic, sometimes they're friendly, right? And it's just kind of how those debuggers are. and tell you how to fix it, hopefully. And if not, then you're running to Google to look it up, or your textbook, or your friend, or your instructor, or whatever. And it's okay to reach out. Now I'm noticing in this PowerPoint, you guys probably noticed it too, that whenever they created this, they were using a different IDE than the one that we installed, right? In fact, they were using one called Wing. And here's the truth, folks. There are many IDEs that support Python. For those of you that have worked in Visual Studio, for example, some of you may have. Visual Studio is great at supporting Python and now has a complete set of Python tools built in. And it uses the same core Anaconda libraries that the Spider IDE does, that hopefully if it finishes installing here we can get to in just a second. But you're going to see that commonality of how these IDEs work. So all of them will have that coding area that you see right here. Somewhere you type, color coding, everything. You'll have a console or output window that's kind of like this, and often they'll have other areas of the screens that are designated to either file or object management, help screens, and other little resources that you can pull in. Those are typically the three main panels that you see. A better IDE is highly customizable, where you can start pulling off the pieces, so you can take these panels and you can like move them over to a second screen, where you can change like the size of your fonts or whatever, even sometimes the whole look of the environment, and sometimes that's highly customizable. So what our goal is going to be here is, as soon as Spider finishes loading up, and I'm not very patiently waiting for this, obviously, because I started the install, like 10-15 minutes ago, and it's still going, is to write this program. But let's take a look at like the structure of it before we get to the actual coding. And if you guys can get Spider up and running, you can go ahead and start typing this in. That's absolutely fine. But take a look. The first thing that you're going to notice on that first line, and I kind of like the fact that this book jumps right into explaining what a comment is right off the bat. They're not afraid to do it. Some books wait a while before they show it to you. But that first line is what we call a comment. You notice how it's like green, right? And you notice at the beginning of the line there's a pound sign or a hash mark, right? If I'm a good coder, you're going to put lots of comments in your code. Why? Well, first of all, so you remember what you did, right? So like, why did I do this? Now, I can tell you, I've written lots of code in my life, and in the past I was horrible about commenting because I thought it just wasted space, right? I'm like, that's going to make my file really huge and it's going to run inefficiently. Wrong. The truth is, when your comments are in your code and the program actually runs, those are all ignored. It has no impact on the performance at all. It's ignored, it's removed. But when you come back 10 years later and you want to look at a piece of code, and I'm going to show you an example here, and this is actually kind of humorous, and I'm hoping you guys find humor in it. Oh, and of course it's not on this machine. All right, never mind. But I was going to bring up a program that I wrote about 25 years ago in a language called Pascal. And I put no comments in my code. Fortunately, I was pretty good about how I named the objects inside there, so I knew kind of what I was doing. But sometimes you go back to code that you've written it because you need to fix it or upgrade it or whatever. And then you look at it and you go, oh my God, why the hell did I do this? I forgot. So a tip for programmers, always include comments to indicate what's going on, especially if it's kind of tricky. If it's a print statement, it's like, okay, whatever, right? But if it's something really complicated or there's weird math involved or something, you should put comments in. And it also helps to kind of like break the code up into sections so you can identify it. Next part, they start with the most basic of computer programs, and this that you're seeing on your screen now is a combination of a few different things. Python as a language has built into it what we call built-in functions or methods. And so to explain what that means, the print function in Python is a set of commands that allows you to take that whatever you put in these parentheses will output to the screen or to the console. We didn't have to write the code to do that because there is code that's required to make that happen. We just use it. And a lot of the stuff that we're going to do is going to be like that. But if you find whenever you're working in a language that it lacks a certain functionality, this is where people develop new languages and new things. And the good news is my install is done, that flash on the screen. But that capability is a built-in, so we're just going to leverage it. The part inside the parentheses is what we call an argument. We are passing a value to the pre-built function that will perform the action. But this one expects to print something on the screen. What is it you want to print on the screen? In this case, whenever we use single or double quotes encapsulating something, that's called a string literal. That's what we're going to put up on the screen. We're going to put hello world on the screen exactly as you see it there. If I were to omit the quotations, what would happen? It wouldn't run. If it was math, if I had 1 plus 1 in there, it would do the math and put 2 on the screen because it understands math. But if you just say hello world without quotes, it doesn't know what to do. Okay, so now that my IDE seems to seemingly be installed, you see how excited I am, right? I don't want to learn more, and I don't want to learn more. Thank you. All right, so now it's installed. So I'm going to launch the Spider IDE. And I'm going to do that, folks, by just going to my menu here, and I'm just going to type SPY, because that's how they spell it. And we're going to launch it. Now, Spider, like all IDEs, are pretty complicated pieces of software. And it's not like launching Notepad++. It does take a little bit of time to load on most systems. If you shut it down after you've run it and then relaunch it again, if you have not rebooted, it does leave what I call a little bootstrap in memory, so it will reload much quicker. And I don't know if you guys are like Photoshop users or anything like that. Like Photoshop's kind of like that. First time you launch it, you're waiting 2 minutes, and then you come back to it later and it's like 10 seconds. So Spider is kind of the same way. All right, so welcome to the Spider IDE. I know we brought this up last week and talked about the environment a little bit. And you'll notice right away those 3 key areas I'm talking about. Left side of the screen is the editor window. Bottom right is the console window. In fact, the tab is even marked that way. And I know that on my screen it might be a little hard to read. So if you're watching the video, you might want to go full screen on it to really see it. And then up here at the top, this is where we often look at either our file structure or object structure or helpful information that's attached to certain functions. What I'm going to do to begin with is, I know that you guys in the room can probably see that. I'm going to be really frank. That's hard on my eyes. That's a little too small. And a helpful tip for you guys, I'm just looking around the room right now. Well, 2 of you are wearing glasses right now. If you guys don't bump up your font size, I'm just giving you fair warning, and increase your screen contrast when you're young, by the time you get to be my age, you're going to be wearing contacts and glasses and probably half blind. Because if you're in the habit of looking at really dim screens and really small fonts, your eyes will wane over time, and especially if you don't break that 18-inch focus from the screen and change your, look at things that are distant as well as things that are close, your eyesight will suffer. Please do yourself the favor, make your fonts bigger. So what I'm going to do here is I'm going to find where the preferences are for this thing. And I am fairly new to this IDE. And there's the preferences. And let's see if we can find where to change. Oh, it's right on the top, on the first tab. And it's at a 10-point font right now, or 10 pixel font. And you know what? I'm going to bump that up to like a 14 for both the rich text and the plain text. And then I'm going to click apply. So you can see all the fonts just got a little bit bigger. So people watching the video are now thankful because they can actually see what I'm doing. But once again, my eyes are happier too. All right, the first thing I'm going to do is I'm actually going to kind of blow away all the stuff that they have in there. You guys notice I'm leaving the top line. Could I get rid of it? Yeah, you can get rid of it. All right. But what they're doing there is it's just a little indication. Does anybody have any clue what UTF-8 means? All right. Some of you have done HTML, and like you've done HTML, like one of the things they have you do is, character set equals UTF-8, and that's just kind of the standard ASCII key code. That is usually implied in most environments, but if you start working with different languages and stuff, then sometimes you need to change it. Chances are you probably never will need to change it. I'm going to get rid of it. I'm just making mention of it. I am going to copy what they did in the book. I'm going to start with a comment. So I'm just going to type in, this is my very first Python program. Yippee. Yeah, you know what? Have fun with it. The other thing that I might suggest that you do, this is just a suggestion. Some teachers, when they have you turn in homework, and you guys tell me if this sounds familiar, if you're turning in a code file, make sure your name is at the top with the name of the assignment and the exercise number and the page number and the date and the file name and, your firstborn social security number, something like that, right? And then also when you save the file as this very specific name. Frankly, I don't care. I'm just going to be real frank with you. I used to do that in the past. And then I realized, well, I don't really want to manage that. Because really, if you don't name your files well, and if you don't put in good comments, it's going to come back to bite you, not me. So for me, when I see it in Blackboard as an assignment, it doesn't matter what it's called. That's why I kind of joke around and type whatever. Because I can still grade it whatever you call it, right? You turned it in for Unit 1, Chapter 1, well, there it is. That must be Unit 1, Chapter 1, otherwise you wouldn't have turned it in there. So I don't care what you call it. However, all right, other teachers are not wrong at the same time. I don't know what file systems they use. I think it's kind of an antiquated approach, frankly, to force people to name stuff certain ways. But for your sake, you should name it in a way that makes sense. That's why I did the thing earlier in class. All right, let's go ahead and type the command. I'm going to type print. And the classic first program you're supposed to write. So if you've never done computer programming before, do this because you have to do it at least once in your life. You're supposed to go, hello world. Why? Because the very first computer program, that's the first output they did. So we are following that fine tradition. Now, do you notice what happened as I was typing? In fact, let me kind of just backtrack. You saw it all color code, right? So here we go. Change lines. Typing P, R, I, N, T. Color coded right away because it recognized it as a keyword. And you see how it highlighted yellow, right? Now this IDE, you notice what it says up here? Here you can get help from any object by pressing Control-I in front of it, either in the editor or the console. So if I go to the front of that word and do a Control-I, watch the little help window. It tells you how that works. Okay, print isn't a difficult one, right? But when you get to some that are really complicated, frankly, folks, no programmer remembers all the keywords or how they work. Nobody does. Not unless you do it every single day. So you might pull up some rare function or whatever, and like, how does this work? So you just do this and go, oh, that's how it works, all right. It's like using a weird feature on your car. Sometimes you have to go to the manual to figure out where to put the oil in. Okay. All right, so then I'm going to go back in. Now I'm going to add my parenthesis, and notice how it automatically typed the second one for me. Not because I'm stupid, but because it wants to make sure that I don't make a mistake. Because if I skipped it, it wouldn't work. I'm also going to put into double quotes and type. Now I thought it would put in the closing double quote, but oh boy was I wrong. So I guess you got to remember to do that. Now that argument list pops up, and that's to remind you of what types of things you can put in there. Yes, I can put in hello world with a double quote or a single quote. Doesn't matter, as long as it's consistent and they match. Okay? So whenever we're doing a string, single quote or double quote. There are reasons why you choose them certain ways. My preference has always been double quotes first, single quotes second, but some people are the converse. It doesn't really matter. All right, so if you've done that, save your file. Let's do that first. So what I'm going to do is I'm going to click Save. Okay, well, it just saved it. It didn't even ask me where. Where the hell did it go? Well, here's where it went. It went into whatever directory Spider's in. You know what? Bad idea. Okay? Why do you think I talked about file management before? I'm going to go now to the menu and I'm going to do Save As, and then I'm going to find that folder that I created for this class. And for me, that was in my Google Drive, in my Python folder, and remember I made a folder for 2019 fall, and then I'm going to make another folder inside here for Unit 1. Because that way, when I come back, wait, this is Unit 2 though. Or maybe I should say just Chapter 1. You think Chapter 1's better? Yeah, let's do Chapter 1. Whatever makes sense. So Chapter 1. So when I come back next year, I know where to find stuff. Just simple as that. What am I going to name it? Well, I'm not going to name it temp py. I'm going to call it hello.py. Now, if I don't put in the .py, it will add it automatically. It's kind of a no-brainer, but maybe not. So now it's saved. Now I can come up here and I can hit the play button. Now this is kind of silly, right? Almost. When I hit that play button, notice as I hover over it, what does it say? It's going to run the file, and then in parentheses it says what? F5. So here's a tip for y'all. When you're working in IDEs, many IDEs, when you press F5 on the keyboard, it's equivalent to pressing run. Just saying. Not that you have to do it that way, but sometimes keyboard shortcuts are a whole lot faster. All right. So now we have the run settings that pop up, and you notice there's a little option here at the bottom that says, always show this dialog on a first file run. And for right now, I'm going to leave mine unchecked, although I will be tempted to turn this off because I find it kind of an annoyance. I just want it to run. But let's take a look at the options really quick. In the top category, it says console. It says execute in current console, meaning the window that we can see right now. Yeah, that's a good choice. Or in a dedicated console, or in an external system terminal. So if I wanted, I could make this run at the Windows command prompt or PowerShell. I'm not going to choose those options. Okay, other general settings. Remove all variables before execution. That's if they're stored. Directly enter debugging. Blah, 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 blah. I'm just going to leave all these alone. There's no reason to trigger them. There are some times where you might want to come in here and adjust these. But I don't see the purpose. The other one is the working directory settings, the directory of the file being executed. Well, that makes sense to me. But once again, there are times that you want to switch. All right, I'm going to go ahead and click Run. And then over on the right there, what did it do? It told me what it was doing. First of all, it says, I'm running the file. It told me exactly where the file was located. Believe it or not, for as silly as that seems, that's actually can be very helpful. Because what if you, I hit save and I don't know where it went. Well, there it went, okay? And then it also indicates the working directory, the one where we're actually going to run the program, is in the same spot. And then here's the program. Hello world. Everybody get this to work? Right, it's pretty easy. Here's the beauty of the homework we're going to do in this chapter. All of it is basically just doing the print command. Just getting you comfortable with one command and writing the programs and working in the environment. Trust me, it'll get harder. So if you think this is too easy, it's okay. Another thing I want to show you guys about the console in a Python environment. How many of you have done any JavaScript programming? A lot of you. Okay, so you probably have seen this. When you do JavaScript programming, you kind of do the same thing. You can write your code, link it up with your web page, and then it runs in the browser. And then your teacher should teach you that there's a console inside the browser where you can go to and you can actually type commands. So if I just type a Python command here, and press enter, guess what it does? It runs. You know what the cool part about that is you can, like, will this work? You know, will print 1 + 1 work? Oh yeah, sure, that's right. Okay, now I can add it to my code. So you can try commands to see if they even work before you put them in your code. All right, so we have a console. So this is the beauty of an interpreted language, is it doesn't really need to be compiled, it just runs. All right, folks. What I'm going to turn you to now is the actual homework. So we're kind of shifting modes here. All right, and I know our time is waning, but at least I got to exactly as far as I thought I would. So we are in Unit 2. And I want to explain the methodology for doing the homework. Because, right, if you want to get an A in a class, you should know what the instructor wants. So let me show you the anatomy of how I even put this on a page. All right, whenever I have an assignment like this, a programming assignment, you're always going to see this sort of a designation. I usually color the title, which is the link to submitting the homework, blue, so you realize it's a link. This is kind of like the web designer in me, and I apologize for that. The other thing I do is I always throw that silly little icon in, so it flags to you that you need to do this. Okay, there's points attached. The title, right after that icon, the part in bold and green, that's the crux of what you're doing. Complete Chapter 1 programming exercises, and I went through and I hand-selected certain ones, and if you count them, there's a total of 8 of them. If you click on the title, you will discover that there's 4 points attached to this, and the due date. So the due date is 9 days from today. Next week, 2 days after class. It gives you the opportunity to come to class with questions, fix it, and turn it in. That's my strategy. But going back to where we were, the next part of what I want to point out is the details, right? So I want you to be successful. And the way that you're going to be successful is to give me what I'm looking for. So please read the instructions. Chances are the instructions for all the homework will be the same. But I still like to detail it because sometimes I'll change it. Okay. So it says make sure to complete these tasks. Create a folder for the Chapter 1 exercises. All right, hopefully you did that. Save each program as a separate file using a meaningful file name for easy identification. I'm not telling you what to choose. Choose whatever works for you. Simple as that. All the programs will end with .py. What I don't want you to do is go to Spider, right? Where the heck is it? There it is. Write this program, and then get it to run. Great. Then come back in here and write another program over the same file. Create a new file. Just do a Control-N. Create a new file in the environment and start over and save it as a separate file. In fact, the first step before you do any coding after you create a new file is to go to File, Save As, and save it with the right name. My suggestion, if you want a suggestion on how to name it, I would probably say exercise 1-1. Why don't I use a dot? Because that's used for file extensions. I mean, you can still use it actually, but exercise 1-1, and I might just call it that and leave it at that. Frankly, it's up to you, but that's what I would recommend. So do that. Follow the directions for each exercise carefully and create each program as described. So in other words, you need to read what the author is asking for and do exactly what is being asked. If there's a variation on it, I'll let you know. And in some cases, like there's one where it says print your favorite poem. Well, you could do song lyrics, I guess, that would be cool too. Or, create a poem, roses are red, violets are blue. All right. Also, test the program to make sure it works. Don't just type the code and never hit run. Right? Because I do get students that do that. Right? It's like, well, that's great. You wrote all this code, but did you even try it? No, of course you're going to try it, right? So make sure it runs. Fix any errors if you get any. As you complete each program, use the snipping tool to take screenshots. You're going to take those screenshots and insert them into a Word document. Does anybody want me to demonstrate that again? You guys are all cool with it. You're all experts, right? And remember, try to set up your screen so that if you do a screenshot where you're getting the console window and the code all at the same time, because most of our programs here, that's what it's going to be. If you're on like a 3,000 by 2,000 pixel display, please don't give me a screenshot of the whole damn screen. Please, because when you put it into a Word doc, I won't be able to read it. You know, what you want to do is like what I did last week, where I would take this, I would make the window significantly smaller, but make sure that I could also see everything. And then I would just screenshot just that bit that I need. And I said I wasn't going to demonstrate, but I'm demonstrating anyway, so that's just my nature, sorry. All right, and I would get just at least the part I need. You gave me that much, it would be fine. And then when you take that screenshot and paste it into your Word document, please also say, this is exercise 1. It went pretty well. Or, oh my God, it was a nightmare, help. And make it like bold and red. You know, I get those. But you know what? That's a communication mechanism for us. Because if I get all of you giving me the same response on one of the exercises, I might just throw it out. You see what I'm saying? So it's important to me as a communication tool. All right. Okay, finally, when you're done with the code, so you're going to have a Word document that you've created with a screenshot, and you'll upload that to Blackboard. So maybe I'm just going to go through the cumbersome process of doing this, and I'm thinking, you know, out loud here, kind of more for the sake of the people that might take this course online and watch the video. So this is the process I would use. So homework, you might want to put your name on it, you know, too, maybe like name. Homework, chapter 1. All right, exercise 1. I would go to Spider, get my snipping tool. I'm doing this as fast as I can. Grab my screenshot. I got my hello world in there. I'm going to click the copy button, go to Word, paste it in, right? I'm going to save it. Where should I save it? Wherever. Wherever is meaningful to you. I'm just going to throw it on the desktop for right now. All right, so there's my Word file. And then I'm also going to go to the folder where my code is. And I'm going to do this. Now, you guys will notice that this part is not necessarily required if you read the instructions carefully. It says zip the folder containing your work and upload to Blackboard. This will serve as a backup and allow your instructor to double check your work. So I guess I am requiring it. I guess in some classes I make it optional, and in some classes I require it. I guess at this point I'm going to require it because the programs will all be small and it will serve as a backup for you.
So you're just going to download the files and run them, right?
Tom, you know, for an assignment like the ones that we're doing in chapter 1, it's all prints. There's no logic we're testing. So your prints either worked or not. So I can look at a screenshot, look at your code and go, okay, it's fine. And the truth is, even for more advanced classes, just a quick glance at the code for me is enough. But there are classes where I do have to unzip it and run it. You know, if I have like questions about it in any way, shape, or form. So what you guys will do is wherever your code is, grab that.
I mean, the only reason I said that is because I just wanted to make sure I didn't miss some magic feature of the IDE where you're auto-loading it into there or something out of...
No, that's not at all the case.
Okay.
It's not at all the case, but you know, it's a valid question. So I'm going to take my code folder here, folks, and I'm going to right-click it in Windows, And then you just compress it like this by choosing compress zipped folder. I'm hoping you guys have done this process before. Okay? In fact, I was kind of being dumb before with my screenshot document. Where the heck did I put that? All right. I guess I called it name. That's not really a great name. I'm going to drop that in here too. And of course it's open, so let's close it. All right. And then when it's time to upload to Blackboard, and this part, for as silly as it seems, please follow this part for me, because it makes my life a whole lot easier when I grade. When you're submitting the work, and I'm going to zoom out a little bit so we go back to kind of like the view you guys have. When you're submitting your work, please do it like this. The files that you have, you can actually drag and drop them. I don't know if you guys are aware of this, like this. You can just take the document first. Document first. You guys catching that? Don't put the document inside the zip. That does not make my life easy. That makes my life hell. Actually, it makes it a little more difficult. All right. So document first. That's attached, so you see it listed. And then I'm going to drag the zip separately in there. And then if you want to write some comments, where I prefer that you do it is here with write submission instead of here. Write your comments here. And then when you're all set, hit submit. Question?
Yeah, for the Word doc, because the assignments, do you want us to make a separate Word doc for everyone?
Excellent question. So if it's a set of assignments listed all together, one Word doc works. Yeah, you don't have to make like if there's 5 exercises, don't create 5 documents. One document is fine. However, if it's 5 exercises, you probably will have 5 separate programming files, which is why I want you to zip them. All right. Thank you, everybody. We got just as far as I hoped. We'll see you all next week.
See you later, Ty.
Take care.